All right, so now that we know when the essential limit theorem can apply, how do you actually apply it? So we're going to have a couple of cases that we can look at when we're applying the essential limit theorem. So the first one says for the individual value, when working with an individual value, so n is equal to 1, from a normally distributed population, use the methods of 6.2. So we're going to be using our standard z-score formula. So x minus the mean divided by the standard deviation. So we're going to use that like we did back in 6.2. In the case of a sample of values, when working with a mean for some sample n is greater than 1, be sure to use the value of sigma over the square root of n for the standard deviation of the sample means. So we're using this formula here. Now the one thing to keep in mind is they like to use this x bar, but if that's throwing you off or it's confusing you, think of it as x. That will work just as fine. And we're going to see this in action in just a minute. So, but the big thing is that the top really is the same. You got x minus the mean, but the bottom, you have this modified standard deviation on the bottom. So this is, I like to call this the modified z-score formula. So I'm going to refer to it that way. The modified z-score formula has this modified standard deviation in the bottom. All right, so we have a couple of processes. Let's try them on some examples. So our first one says assume that SAT scores are normally distributed with a mean of mu equal to 1518 and a standard deviation of sigma equal to 325. If one SAT score is randomly selected, find the probability that the score is less than 1500. So one SAT score is randomly selected. So what's the value of n? So this tells us that n is equal to 1. So this is our individual case. So this is the same as what we did back in 6.2. So now if I draw a quick little diagram just to make sure we have it down. Now our mean is 1518, so we know that's in the middle. And our special value of x is this 1500. So we know that's over here somewhere. And which side are we shading? It's less than. So we're going to have to shade on the left-hand side. So there's our diagram. So remember, the diagram is just going to be beneficial for determining if your final answer should be small, meaning less than 0.5, or more than 0.5. So that's all that's good for. So in this case, we should know it's going to be small. It's less than 0.5. So now let's go through our steps. So we have our value of x of 1500. So we want to convert that to a z-score. So we're just going to plug that in to our standard z-score formula and divide it. So if we divide that on our calculator, what do we get? So 1500 minus 1518 equals a negative, divided by 325 equals, so we got negative 0.055, blah, 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 blah. So we're going to want to round that to 2 decimal places, so make sure you round it to 0.06. So negative 0.06. And so now we can get our probability from that. So we're going to want to use our negative z-score table, and we're going to use negative 0.06. So there's negative 0.0 way down at the bottom here on the left. And so negative 0.06 is, well, let's make sure we get the right column. So we're the 4th column from the right. So we're in this column here. All the way down to the bottom. So 4761. So 4761. So that is your answer. All right. So again, that's the same that we did back in 6.2. So let's see what happens when we have a different size sample. If 100 SAT scores are randomly selected, find the probability that the scores have a mean less than 1500. So let me just explain. If we wanted to analyze those 100 scores individually, that's going to take a long time because you have to analyze every single one of those. But if we batch them together, the only way we can analyze that batch is by looking at something that represents them all, and that's going to be the mean. So if we looked at the mean, that's a single value that we can analyze. So that's why they use that X bar notation, because you're averaging those 100 values, not just looking at them individually. So the nice thing about this problem is that we have a lot of the same stuff as the previous one. We still have a special value of 1500 we're analyzing, and it's less than that. So our drawing is actually the same as this. So we don't even need to draw it. Now, like I said, technically speaking, this is X bar because the average is a single value versus 100 values. I'm not going to quibble over that. I'm not going to penalize you for that if you don't put an X bar in your work. If you want to, great, but don't worry about it. From here, though, we got to be careful because now n is equal to 100. So that we have to be careful with. So we still have the same top, but the bottom is a little different. So we get the square root, or 325 over the square root of 100. Now, when you simplify this down, I would be very, very careful in how you do it. I would actually simplify this down first just to be safe. And if you do that, the square root of 100 is 10, so this would be equal to 32.5. So when you do all of the math, we already know we're going to get negative 18 on top. And if we divide it by 32.5, it's very similar to what we had up above, but now the decimal place got moved because the decimal place got moved down here. So our z-score is negative 0.55. And so now when we go to our table, negative 0.55. So 0.5 is in this column here, and negative 0.5 is right down close to the bottom. So it looks like 2912. 0.2912 should be our probability. So what do you think? Not too bad so far, right? Just got to be careful of that value of n. When there's an n, we need to use the modified z-score formula. And just be careful when you simplify it down. It's really easy to make a mistake. All right, so let's try C, and then we'll pick up the next example in the next video. If 25 SAT scores are randomly selected, find the probability that the scores have a mean between 1550 and 1575. Now, the first thing we notice is that n is equal to 25. And now some bells and whistles should be going off because remember, 30 is that magic number we talked about on the previous page. We're not at 30, we're below it. So are we stuck? Can we do this problem at all? Well, let's go back to the top. Go back to the top. What did they tell us? Assume that SAT scores are normally distributed. So the population was normally distributed to begin with. And if it's normally distributed to begin with, it doesn't matter what n is. It could be small or it could be large, and that should still give us a normal distribution. So we're fine. So even though it's small, we can still apply the central limit theorem. And if we wanted to give a drawing here, so we got our 1518 in the middle, 1550 is over here somewhere, and 1575 is right there. And we're looking at this tiny little piece, so our answer should be small. So let's see what we can do. So we're going to use our modified z-score formula because n is not 1. So 1550 minus 1518 divided by 325 divided by the square root of 25. Now, depending on your calculator, if you have a graphing one, obviously you can do this much easier. In fact, let's do it on a graphing one just to show you, if I can turn it on. All right, so there's our graphing calculator. So if I wanted to be really careful how I do this, I could use parentheses around the top and parentheses around the bottom. And that way I know it's doing those things first. So if I put parentheses, then 1550 minus 1518. So there's the top, divided by parentheses, 325 divided by the square root of 25. Oops. I'm going to delete that. And then put my, so that wraps the entire bottom. And if I hit equals, I get 0.4923, blah, 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 blah. So remember, this is a z-score, so we just want those first two decimal places and round up if you need to round up. So 0.49. And then we can go to our table, get our probability. So now we want the positive z-scores. So 0.49. So there's 0.4. There's the 0.9 part. So it looks like we're 6879. So 6879. All right, and then let's do it for the other one. All right, let's do it on this one. Let me move it over here so we can see a little bit. So now the top, 1575 minus 1518 equals 57. And now the bottom, remember, if we wanted to do the bottom separately, we could do it in parentheses on here too. So I hit divided by, and then parentheses. I could do 325 divided by 25 square root, close my parentheses. So that's the bottom. But then I got to hit equals to finish it off. So we can see that this should be 0.8. That 6 is going to bounce that 7 up. So 0.88. All right, so now we got to go to our table and get our probability. So 0.88. So there's 0.8. There's the other 8. And so that gets us to 8106. All right, what's the last step? Yeah, we got to subtract them. So our answer is going to be 0.8106 minus 0.6879, which gets you 0.1227. So there's our answer. Again, not a lot of extra steps or new concepts per se, but it's just adding a little bit of a twist to the process, because now we're looking at values where n is not just a single value we're pulling out multiple values. So, all right, so let's stop there, and then we'll pick up the next example in the next video. See you in a minute.